Hey guys, let's go over some basics about organic chemistry naming. First, I want to talk about the main chain itself. How do I name that chain of carbons? Basically, we're going to take the prefix and the suffix and stick it together. Nothing in the middle. Don't tell your English teachers. Prefix, suffix equals word. So prefix is going to be based on the number of carbons. The catch, the trick that you got to watch out for is that you're always basing the name off the longest chain, which may or may not be the longest chain just from left to right. You got to watch out for your branches. Once you identify the longest chain, you're going to name that hydrocarbon after that number of carbons. And there are some unique prefixes for 1 through 4. If I have just one carbon, the prefix would be meth. For 2, it would be eth. 3, prop, and 4, bute. But then you're going to get into all your normal prefixes. Pent, hex, hept, oct, non, all the normal ones. But for 1 through 4, it is unique to organic naming. Meth, ep, prop, and bute. The suffix, or the ending of the name, is going to be based on the bonding. So if I just have a single bond, I'm going to end with ane. If I have a double bond, I would end with ene. And if I have a triple bond, I would end with yne. We're going to get into a lot of different types of groups that could come off of these main chains. So I also want to mention just some general overall rules. The very first rule for numbering our order of functional groups, you can see how some of these examples have numbers involved. The main numbering rule is that you want the lowest overall numbers. So if you could number something 2 and 3, as opposed to numbering from the other side and getting to numbers 4 and 5, you would rather go with the numbering system that produces those numbers 2 and 3. Lowest overall number system is the main rule. Sometimes there's a tie though, and so if you're not sure which end of the molecule to start numbering from, like because it would both be the lowest number, the tiebreaker is alphabetical order. So for example, an F chain, like an ethyl group off of the main chain, would be numbered first over a propyl group chain. So you would go by the alphabetical order of the functional groups. That would be your tiebreaker to determine which one would get the lowest of the lowest overall numbers. This is going to get us our main name of the chain. What I'm going to be using as I go through the functional groups is mostly propane. So prop would have 3 carbons, and because it's got the ane, I have single bonds. Remember your saturation rules for your octet, that it would be surrounded by hydrogens. Keeping in mind if there's a double bond, you may not need as many hydrogens. So we're just going to be basing our functional groups off of normal propane so we can actually focus on the groups themselves. All right, let's start with what if I just had a branch off of the main chain that was still just made of hydrocarbons? So it's still just a carbon chain that's branching off of the main chain. Maybe I should note that it's a branch. So you're going to name the chain with the number carbon prefix. So for example, if that carbon branch had 1 carbon to it, I would call it the methyl group. 2 carbons off the main chain would be an ethyl group, and so on. And then notice I mentioned kind of an ending already, the YL, indicating that it's a branch. So what would 2-methylpropane look like? So I always draw my main chain first. So let me first draw my 3 carbons. The number in front of the functional group always tells me where to place that functional group. And then I can tell because of the prefix meth, it would only be 1 carbon. Always when you're done with your carbons, saturate the compound, meaning surround them with hydrogens. And that would be our 2-methylpropane. Now it is possible for the branch to circle around itself. So then you're just going to get a circular, I guess I'm kind of repeating myself here, circular structure, a circular carbon chain. And on the name, you want to indicate that with the prefix cyclo in front of the carbon number prefix prop. So cyclopropane tells me I have 3 carbons single bonded in a circle. So I would show that it actually kind of would look like a triangle for the propane. And then since each of them already have 2 bonds, you would only have 2 hydrogens off of each one. So cyclo kind of shows it doubling up on itself. Now, there are specific derivatives, and I have them marked throughout here with these big lines in front of them, that are all going to be based off of benzene, which is a specific type of circular structure that has something special called conjugated double bonds. It's based on a 6-carbon ring where every other carbon is double bonded. Now, you don't draw it like that usually. Because of resonance, we know that these double bonds would actually be swapping back and forth. So you usually just draw that and show that with the circle in the middle. Now, without that circle in the middle, it's just cyclohexane. But when you show that circle in the middle, you're showing those double bonds resonating amongst the structure. And so you have benzene. And so we're going to look at how some of the different functional groups attach to benzene as we go through this. All right, now let's look at a group called halides. So halides are based on halogens. So you're going to take your carbon structure, and as I go through this, I'm going to use R to indicate any type of carbon chain. In my examples, I'm using propane, but it could be any carbon chain. And it's going to be attached to one of the halogens. So for example, fluorine, or maybe we could have a carbon chain attached to bromine, carbon attached to chlorine, carbon attached to iodine. One of our halogens have that structure of the carbon chain with the halogen attached. What you're going to do is see the name of the chain kind of mentioned. So if it's fluorine, you're going to see fluoro as the prefix. If it's iodine, you would see iodo. For bromine, you would see bromo, and for chlorine, kind of running out of room here, you'd see chloro. So obviously those are tied to the respective halogens. So let's look at 2-bromopropane, starting by my carbon chain of propane. The 2 tells me where to place my functional group again, and because it says bromo, I know it would refer to bromine, Br. Now, when I'm done, I'm going to saturate the carbons. But a halogen is not part of the saturation. As a matter of fact, we would assume that that halogen is surrounded by lone pairs or electrons, not hydrogens. So it's only the carbons that get saturated, and the bromine would be there in the middle. 2-bromopropane. All right, on to our next functional group, an alcohol. So an alcohol would take some kind of carbon chain and attach a hydroxide group, or an OH, and you're going to change the ending of the name to OL. So you still have to say where that alcohol is formed, though, so there would be a number in front as well. So let's look at our example 2-propanol. Propane still being the base molecule, so I'm still going to draw my 3 carbons. But because I can see the OL, I know I'm attaching a hydroxide group. The number is going to tell me where, which again is in the second or middle carbon, and I'm going to attach the OH. Saturate the carbons, but leave the functional group alone. It's already assumed that you understand the octet rule and that you understand the bonding. So you're just writing the OH, and everybody would read this as that the carbon is attached to the oxygen, and then that's attached to the hydrogen. The oxygen would have 2 lone pairs. Like, all of that bonding is understood. You just have to show where that functional group is found. In this case, on the second carbon, having that functional group be the OH group. Now, when you attach it to benzene, you call it phenol. As a matter of fact, this prefix PHEN usually refers to benzene. You can even have a phenol group where you attach the benzene as a branch. So phenol would have my benzene, 6-sided ring with the circle showing the resonance, and then at some point we attach an OH group. And when you have the alcohol group on the benzene, you call it a phenol. All right, moving on to a new functional group, an ether. So with an ether, you have your carbon chain with an oxygen interrupting it, meaning you have carbon on either side of the oxygen. Oxygen just dead in the middle. So there's two ways that the name could change. There's two versions of this naming system for ethers. One is that you have the phrase or syllable, I guess I should say, oxy, just in the middle of the word, where on either side of it, you're referring to whichever functional group or whichever hydrocarbon chain you have. The other thing is you could use branches, so the YL version of the organic compounds, and end with the word ether. So either one totally valid. So let's look at an example here. I'm going to give it to you both ways. Methoxypropane, so showing the meth and the prop as my two functional groups, oxy in the middle, or methylpropyl ether, showing the methyl and the propyl as the two functional groups, and ether at the end. Either way, we're going to draw this the same exact way. Meth, I can tell I would have one carbon, and then either from the oxy in the middle or the ether at the end, you can tell there's an oxygen interrupting the chain. And then propane, propyl, shows 3 carbons after that. And then you would saturate only the carbons, not the oxygen. The assumption would be that there's lone pairs on that oxygen. So that would be our ether, going from either naming system. Single carbon, oxygen interrupting it, and then the propane, or the propyl group, I should say. All right, onto probably one of the more complicated functional groups, carboxylic acids. So a carboxylic acid is going to take your carbon chain, and it's going to attach a double bonded O and an OH. So there is a very special structure to that. Actually, let me make a little room to draw it a little more clearly. So typically we would write this in the R version as ROOH. These are our little choo-choo molecules. So the carbon would carry a double bonded O and an OH. And that carbon could be part of however long the chain is, which is why the R is used. Double bonded O and the OH. And the reason it's called an acid is actually because the H from the hydroxide is typically lost. So it does classify as an acid. It's donating a proton. When you change the name for this, you're going to change the ending a lot. ANOIC as the ending. Kind of like how we changed the ending to the OL, but a much bigger change at the end. And you're going to add the word acid to the end. So here's our example, propanoic acid. So again, based on our 3-carbon chain. Now on the last carbon, prop includes that carbon that's used for this. We're going to add the double bonded O and the OH. Whenever we do that, by the way, that automatically makes that carbon the number 1 carbon. So if there were other branches, we would be numbering backwards. Because of how heavy this is, it typically goes on the end of the molecule when we draw it out, and then you're just going to number backwards if there's other stuff attached. There's our propanoic acid. Now this gets really tricky with benzene. Remember that benzene has conjugated double bonds. Every other bond in benzene already is double bonded. So how am I going to already have double bond and single bond, 3 bonds on a carbon, and then attach another double bond for the O and another single bond for the OH? No carbon can handle that many electrons. So what happens instead is there's a separate carbon that's brought in to carry the double bonded O and the OH. Now, that separate carbon does not go into the name at all. There's no methyl mentioned. There's nothing about an extra carbon going in because organic chemistry assumes you understand the octet rule. There is no other way to attach a carboxylic acid group to a benzene without having that extra carbon. So it's just automatic. Don't over-apply that concept because if it's just a normal chain, then the carbon that's in the name is already counting. You're not adding an extra carbon in that case. You're only adding the extra carbon for the benzoic acid. All right, let's wrap this up with some nitrogen-based functional groups. So amine and amino are very similar. They're based on nitrogen. The difference is an amine is going to have nitrogen at the center, whereas the amino is going to have an NH2 branch. So both of these are based on the ammonium group, so NH3. The catch is one of the H's has to be lost, NH2, in order to attach to the functional group of the carbon. So whether that's happening to a long branch or not is the difference between amino or amine. So when we change the name for an amine, you would have whatever the branch is first. So in this example, methyl. And then the word amine is actually the root of the name, kind of like when we did the ether up here. If you're using amino, it's just a prefix in front of the name of the branch, 2-aminopropane. So let's work through these two examples. With amine, I have the nitrogen at the center, and I can tell my branch is a methyl. So I have one carbon, meth, right? One carbon branch. Now we would automatically assume there are those other two hydrogens. Remember, this came from NH3. So I'm just going to remove one hydrogen to replace it with the carbon. Even as a little attachment, the carbon gets saturated. So you would still have the hydrogens around the carbon. Always draw the hydrogens for functional groups. Wherever they're absent, it's assumed that there's electrons. Always draw the dashes for the carbon groups. So that would be the best way I would draw methylamine. Now looking at 2-aminopropane, I can see that propane would be the main part of the molecule, as it's the base word. And I'm going to add an amino group in the second position. So on the second carbon, I'm adding NH2. Actually, let me draw that where it's a little easier to see. Erase some of these lines. So nitrogen, carbon-based, right? Carbon, carbon, carbon. And on the second carbon, attaching NH2. And now why is it NH2 as opposed to my NH3? Remember, I had to remove a hydrogen in order to attach to the carbon chain. So I'm going to write the H's for functional groups. I mean, going all the way back to the alcohol, right? We're writing the H's that go with functional groups. But then the H's on the carbons can be dashed. So that would be the best way to draw the 2-aminopropane. There we go. And then last but not least, what does it look like if I attach that nitrogen-based group to a benzene group? Then we would call that aniline. So I'm going to start with my benzene. And then I'm going to attach, again, NH2, not NH3. Because the third hydrogen would have to be removed in order for it to jump in with the benzene. So we're attaching the amino, or the NH2, to the benzene. Another situation where once I do this and once I call it an aniline, that right there would become the number one carbon wherever we've attached the NH2. So keep that in mind if you have other branches, that has to be the number one carbon. Two cases where that happens: my aniline and my carboxylic acid, where it has to be the number one. All right, now we've gone through all of our different functional groups and our basics of namings. We've just got to kind of practice putting them together, attaching the different branches in different positions. And it just takes some practice. I hope this overview helps. That'll do it for organic naming.